So, let us go ahead and start looking at the proper derivation of the current voltage characteristics of a PN junction. But before we get to this point, we need to understand a bit of what is going on either sides of the junction. So, this is our PN junction. Okay. So, let this picture be there, but I will use this, and we have a depletion region. So, let me call that as the x equal to minus xdp point, and that is the x is equal to xdn point. Okay. So, we have our PN junction that has got this depletion region in the middle, and let us say we have now forward biased this PN junction. So, VA is going to be positive. So, as I mentioned, a lot of holes are going to diffuse from the P to the N side. Okay, you are going to have a lot of holes moving in there. You are going to have a lot of electrons diffusing from the electron diffusion from the N to the P side, that is the hole diffusion from the P to the N side. And you are going to have a small drift, okay, which we are going to more or less ignore. It is a small drift of electrons from the P to the N side and a small drift of holes from the N to the P side, which we will ignore. Okay. So, for all practical purposes, the diffusion component is the current component, and since these holes are being injected, so all this region is depleted. So, if you look at this boundary of the PN junction, okay, so at x equal to xdn, if you just look at this interface here, what is happening here? It is initially got a very small hole population. At VA equal to 0, the whole population here is very small, right. It is Ni square by Nd. So, just to give you an example, if Ni is, say, for silicon, let us say it is about 1E10 per cc, capital Nd, let us say we have doped it to 1E15 per cc, the N bulk region had about these many electrons if all the donors are ionized, and it has, because of the mass action law which is applicable at equilibrium, it has about Ni square by 1E15, which is about 1E5 holes per cc. So, that is the equilibrium condition, right. So, if you were to not apply any voltage and if I were to just deplete the semiconductor, then this region just after x equal to xdn, which is x equal to xdn plus, at that interface we had these many holes and that many electrons. But the moment I apply forward bias, you are going to have a massive influx of holes from the P to the N side. They are going to move through the depletion region and they are all going to appear here at this interface. So, suddenly the whole population there, which was initially 1E5, is going to spike. It is going to spike all the way up to, you know, a very large number, okay, several orders of magnitude larger, and that number depends on the bias voltage, and we will see what that number is. And because of recombination, this whole population is going to immediately start declining in the semiconductor. So, it is as though you see a huge injection of minority carriers, okay. The holes are the minority carriers in the N type material. So, there is an injection of minority carriers, and this minority carrier population is going to decrease with distance because of recombination, and we have already looked at this phenomena when we looked at the continuity equation and recombination generation mechanisms. Okay. So, if you remember, if you looked at the special case of something called as a low level injection, we already looked at what is going to happen when you have a few minority carriers present in a material, and you know how the recombination controls the population density of these minority carriers with distance. We have already looked at that phenomena, and we are going to be using that relation here. We are going to be using that special case of the continuity equation to analyze your PN junction. Now, this is going to be the overall idea. Okay. We are going to first, so strategically I think it is useful to define the plan for deriving the current voltage characteristics. Again, I should have probably put a slide on that, but nevertheless I will write it out quite neatly. So, the plan for the current voltage characteristics for deriving the IV characteristics of a PN junction. So, what is the plan? The plan is first identify the minority carrier concentration on either sides. Okay, that means it is the injected holes in the N side and injected electrons on the P side. We are going to identify the minority carrier concentration as a function of x, as a function of distance. Okay, we are going to find out what is this function, what is f of x that determines how the population of holes. Okay, so let me call this as delta p on the N side, which is the excess holes on the N side. How does the excess holes on the N side vary with distance? We need to identify this point first. How do the excess electrons on the P side vary with distance? We are going to identify this. And now, since they are going to vary with distance, there is going to be a diffusion current. Okay, there is a diffusion current. So, how do we identify the diffusion current? It is proportional, it is Q dN d delta Np by dx, that is the diffusion of electrons, and Q dP d delta Pn by dx is the diffusion of holes. We are going to then identify the diffusion current components and then add these two current components to get the total current. So, very simple idea. First identify the minority carrier distribution with the distance, and then use that function to differentiate that function and get the diffusion current of electrons and holes. So, that is our strategy, that is our game plan to identify the current voltage characteristics. And we are going to do this by using continuity equation and then identify the correct boundary conditions and identify the correct terms for these two expressions for these two, and then use that to identify the current. Okay, so, the first part of it is to solve the continuity equation. Now, what we have to do is we are going to shift the coordinate system a little, okay, because we are very comfortable with defining an x equal to 0 at the point of injection. Okay, so, what I am going to do is our initial coordinate system, okay, we defined x equal to 0 here at the junction, and then we had at x equal to xdn we had the boundary of the depletion region on the N side, okay, and at x equal to minus xdp we had the boundary of the depletion region on the P side. Okay. So, at x equal to xdn is the boundary of the depletion region on the N side, and at x equal to minus xdp we have the boundary of the depletion region on the P side. So, this was the initial coordinate system. So, that is my x. But now I want to change it, I am going to translate, I am going to create a new coordinate system just to make my mathematics a bit simpler. And in that new coordinate system, instead of x I am going to use x prime or x dash if you like, and I am going to mark the x dash equal to 0, the origin point, at x equal to xdn. So, x equal to xdn corresponds to x dash equal to 0, and this is the coordinate system I am going to use only for the N side. I am not going to use this for the P side. For the P side I am going to use a different coordinate system, which is x equal to double prime, and it is heading off this way, it is heading off in the minus x direction. Okay. So, the positive values of x double prime are the negative values of x. Okay. And x double prime has got an origin located at your x equal to minus xdp. When x is equal to minus xdp, x double prime is equal to 0, and when x is equal to xdn, x prime is equal to 0. So, I am going to define two new coordinate systems of this kind. so that I can write my continuity equation in a manner that I am very familiar with, and it is not going to change the physics, it is just going to simplify the math a lot. Okay, instead of using the x coordinate system and using a translation of coordinates, I am just going to use something, I am going to use this transformation, and we will end up with the continuity equation that we are very familiar with. Okay. So, you will find that the continuity equation for that describes the whole population, the injected whole population on the n side, okay, which is the delta p n on the n side, is this. Okay. So, if you are wondering where this expression came from, I would strongly urge you to go back to the points where we discussed the continuity equation, and you will find that this was one of the special cases discussed, which is the minority carrier, low level injection of minority carriers. Okay. So, here you have your diffusion coefficient for holes, you have your minority carrier lifetime for holes, and delta Pn is the excess minority carrier concentration. Okay. In some sense, what does that mean? It means that, let us say Pn represents the number of holes on the n side per unit volume, Pno is the equilibrium number of holes on the n side per unit volume, delta P, now we have shifted this device out of equilibrium and we now have Pn minus Pno, which is the excess minority carriers per unit volume on the n side, being your delta Pn. So, that is your delta Pn, and clearly the spatial derivative of this term is nothing but the spatial derivative of this term, and therefore, we can write everything, every expression in terms of delta Pn of x dash. So, this is the continuity equation, and we know that the solution to that is given by this particular expression here. Now, the key now is to identify the correct boundary conditions. Now, the first boundary condition we will use is that x dash is equal to infinite, that is, if I have an infinitely long p-n junction diode, if I have a very large p-n junction diode, and if these are my bound depletion regions. So, my x dash coordinate system goes like this. At x dash is equal to infinite, there are no minority carriers present, which means that all the minority carriers have recombined by then and nothing exists. Okay. So, Pn is equal to Pno, that means these two values are exactly the same, and delta Pn is 0. Okay, that is very far from the junction, and that is a very reasonable assumption, because there is no band bending, the semiconductor is going to be like the bulk semiconductor, it has got no idea as to what the junction is doing, etc. And this assumption is something called as a long base diode approximation. Okay. And this term base comes in, it will make a lot of sense when we discuss BJTs, but you can note this down as the long base diode approximation. So, if you say that this is the first boundary condition and apply it to that expression, you will find that the term A automatically has to be 0, because at x dash is equal to infinite, this term blows up. Okay, it becomes infinite, but my delta Pn is 0, and that can happen only if A is 0. So, I cannot allow this term to exist. So, this term has to disappear, and that happens only when A is 0. So, remember, we are looking at the n side, this is not, these expressions are not valid for the p side. We are looking at the holes injected into the n side, and we are using the x dash coordinate systems. We are only looking at the n side of the junction. Okay, so that is written here, but just in case that is not clear. So, what is the next boundary condition? I need to identify this coefficient b, and once I identify b, I have my expression for delta Pn. The next boundary condition is to identify the whole population at x dash is equal to 0. And here I have given you a short derivation, but in short the answer is this. Okay. The whole population, so we have your x equal to xdn, or x dash is equal to 0 coordinate system sitting here, and that is my x dash. So, we have some excess holes injected there and it all tapers down to 0. Okay. So, let me just write this very clearly. So, this point here is my x dash is equal to 0, which corresponds to x equal to x dn. And on the y axis I am sketching the delta Pn, which is the excess holes injected into the n side because of the application of the forward bias. And these holes are recombining and they have got a minority carrier lifetime of tau p, and therefore you see this exponential. Now, what is the hole population at this interface? What is delta Pn at x dash is equal to 0? How many holes were injected into the n type semiconductor? Clearly they have to depend upon Va, because that is the applied voltage, and clearly they have to depend upon the exponential of QVA, because that is what the Boltzmann statistics tells you. But you will find that the expression is exactly given by this particular term here. Again, there is a short derivation. You end up with that expression by simply defining the built in potential as an integral of the electric field. Okay, that is of course with some near equilibrium approximations. Okay, but what this expression tells you is that my delta Pn, which is the excess electrons on the n side, excess holes injected into the n side at x dash equal to 0, which is at x equal to x dn, is equal to Pno, which is the equilibrium hole concentration on the n side, into e to the power QVA by kT minus 1, which means at Va equal to 0 at equilibrium, QVA by kT is 1, 1 minus 1 is 0, and therefore there is no excess holes injected into the n side, which makes a lot of sense. But then if I were to make my Va positive, I find that my excess holes injected into the n side increases exponentially with the increase in applied voltage. So, this is the second boundary condition that we will apply. Okay. And that second boundary condition defines what my B is. So, if you remember, my delta Pn of x dash had two terms. It had an A e to the power x dash by dp tau p, and it had a B e to the power minus x dash by dp tau p, okay, and square root of dp tau p, sorry. And we saw that A has to be 0 because of the long base approximation, but we need to find out what B is, and for finding B we are going to use this condition that at x equal to x dash is equal to 0, my delta Pn is equal to Pno into e to the power QVA by kT minus 1. So, that is my value. So, I substitute x dash equal to 0, that makes this term 1, and therefore B is equal to this particular term here. That is exactly what is mentioned in that equation. And therefore, my complete expression for delta Pn x dash is this particular term, which is this. Now, here I forgot to mention one key component. You will find that this dp tau p has become Lp square. Okay, so that's quite an important definition. dP is the diffusion coefficient of holes, tau p is the minority carrier lifetime, which means it is the average time hole which is a minority carrier would last as a free carrier in an n doped semiconductor, okay, because it is going to recombine eventually. So, it is the lifetime of the minority carrier, in this case it is the hole, and this product, okay, this product of dp tau p is quite significant. If you take the square root of this product, we define that square root as a term called as Lp, which is the diffusion length of the holes. Okay, so, this is something called as the diffusion length. and what it tells you is that it gives you an indicator. So, dP is telling you how quickly the species would diffuse, and tau p is telling you for how much time they would diffuse, and therefore, in some sense this the speed of diffusion and the time of diffusion is got a length component to it. So, but since dP is not exactly velocity, it's dP tau p is equal to Lp square, okay. So, square of this diffusion length, and this diffusion length is an indicator as to the distance through which it's the just like you have a time constant defining the the typical response or a measure of the response of RC circuit, you have Lp defining the measure of the length that the minority carriers are diffused into the material, okay. So, you have Lp being a measure of the speed of diffusion and the minority carrier lifetime. So, I forgot to mention that explicitly. So, you find that this is the expression for the excess holes injected into the N type material in a PN junction diode in forward bias. So, you have this term here which is your B, and you have that term here which tells you an exponential dependence with distance, and Lp is your diffusion length, where Lp is equal to square root of dP tau p. And what is dP? dP is approximately your kT mu by q from your Einstein's relation, okay. But of course, do remember that we are not at equilibrium, we are just off equilibrium. So, you are fine with using these estimates. Alright, so now we have the concentration variation. So, that is what we have been looking for. We have delta Pn as a function of x dash, and therefore, since we know the concentration variation, we can now easily find the diffusion current, and the diffusion current is simply q dP into this derivative, and that is a negative sign because we are talking about holes, and that answer turns out to be this, okay. So, this is the diffusion current. You see that the diffusion current is dependent on x dash, and rightly so, because the concentration profile is varying with x dash. So, what we should be looking at is the easiest way to compute the current in the PN junction. So, if that is the junction, that is the xdn and that is the minus xdp. So, this is the N side, that is the P side, that is x equal to minus x dP, and that is x equal to xdn or x dash equal to 0. We need to compute the diffusion current here at x dash equal to 0, okay, because after this point it becomes a little tricky to compute the total current, because you have a diffusion component and you have the minority carriers moving in, etc., etc., okay. So, we want to compute the diffusion current at this edge due to the holes, we want to compute the diffusion current at this edge due to the electrons, and sum these two diffusion current components to give you the total current. So, at x dash equal to 0, my diffusion current simply becomes this particular term. So, what have we done? Just to summarize the strategy, we have first identified, so because we applied a forward bias, we saw that holes were injected into the N side and electrons were injected into the P side, and we firstly calculated the distribution of this excess injected holes on the N side, okay, and then we used that by solving the continuity equation, and we used that estimate to calculate the diffusion current due to holes in the N side, and in particular we are interested in the diffusion current value at x dash equal to 0, that is at the depletion boundary in the N side material. And with that we have completed all our analysis of the current due to holes. We have still not done anything with regards to electrons, but the electrons follow an exact process, and it is easy to calculate the electron current on the p side as well. So, once again you solve the continuity equation to calculate the injected electrons into the p side, you find this profile, and then you find your diffusion current due to the electrons, and you will find the diffusion current due to the electrons at the depletion boundary on the p side is given by this expression, very symmetric solutions. And therefore, the total current in the p-n junction is the summation of the diffusion current due to the electrons and the current due to the holes, and that turns out to be this expression here, which has got an exponential dependence with the applied voltage. We saw that to be true even in the case of a metal semiconductor junction, but the key difference between a Schottky junction and the p-n junction is that in the Schottky junction it was the majority carriers that were carrying the current, and in the p-n junction it is the minority carriers that are carrying the current. Quite a significant difference, which puts out a difference in the operating speeds of these two devices, but both of these can operate as a diode or can have a rectifying nature in the current. So, this entire term can be treated as a constant, right. So, this is what the charge in an electron, that is the diffusion coefficient of electrons, the diffusion coefficient of holes, ln, which is basically square root of dn tau n, and Lp, which is square root of dp tau p, and PNO, which is the equilibrium concentration of holes in the n type material, NPO, which is the equilibrium concentration of n in the p type material, which is basically dependent on the doping, and therefore, this entire term is treated as a constant, and we will denote that as J naught, not I naught. We are talking about current densities here, J naught. So, that is a typo there in the notes. So, J is equal to J naught e to the power q V a by k t minus 1, and this is an expression that most of you will be very familiar with from your high school studies. Okay. So, this tells you that the current in the p-n junction varies like this, it is an exponential relation, and this is the derivation of the current voltage relation.